So I have started the recording, and I would want to welcome you all to the keynote for this afternoon, and especially welcome to Ken Power. And on behalf of everyone in the CAIN team, Ken, most welcome. It's a great privilege to have you here as one of the keynotes for CAIN 2023. And before I hand over to you, I just want to, for those who might not know Ken, say a few words about you. So Ken is an AI software engineer and researcher. He is currently Director of Engineering at Motional, and they are one of the leaders in robotaxis and driverless technology. Ken leads the advanced projects team there, working on the intersection of architecture, software engineering, machine learning, and compute platforms. But not only that, Ken holds a PhD in information systems from Galway in Ireland. And he has long industry experience also from Cisco, and if I am not mistaken, also from your own consulting work. So most welcome, Ken. Great to have you here. And please share your screen, and the floor is yours.
Thank you so much, Helena, and it's my honor and pleasure to be here. Thank you for your kind invitation and your kind introduction. We've got about 60 minutes together today, I believe, for the keynote part, and we'll leave some time for questions and discussion at the end. But I'd like to start with a prediction, and my prediction is that in this decade, we will see a number of major world cities ban or significantly restrict the use of manually driven vehicles on public roads. So that means literally we will see some cities adopt driverless vehicles on a very large scale. And why? There's many motivations for this. Number one, among those reasons are safety. So many lives are lost each year through avoidable accidents and incidents on the roads, reclaiming space, making better use of our cities, providing better mobility and accessibility options for people that need to travel to different places, making better utilization of our space. And there is, of course, an environmental impact as well, and with an opportunity to save a lot of energy, because autonomous vehicles are very tightly associated with electric vehicles and the evolution of electric vehicle driving. So we'll look at this topic in 4 parts today. The first part will look at autonomous vehicles. Second part will look at emerging trends in machine learning that are enabling autonomous vehicles to operate in the world. In the third section, we'll look at trends in software and systems engineering and compute platforms and hardware and silicon that are enabling all of this. And then in the fourth section, we'll bring it all together to tie it together with some of the themes of the CAIN conference. So when we talk about autonomous vehicles and autonomy in general, it's important to understand that there are different levels of autonomy, and there's a scale from level 0 to level 5. This is one popular scale for understanding different levels of autonomy. So level 0 is a regular vehicle. There's no autonomy. The human driver is in full control and is responsible for the entire operation of the vehicle. Folks are going to be familiar with companies like Tesla. Tesla operates typically at level 2, level 3, somewhere in between. And a key distinguishing characteristic of a vehicle operating at level 2 is there is still a human driver that needs to be ready to take control of the vehicle in certain conditions. Then there are many other companies, ourselves included, who are operating in the level 4 plus space. And in a level 4 vehicle, the key distinction between earlier levels is there is no human driver in the vehicle. The goal is that the vehicle operates itself autonomously. There's high degree of driving autonomy in the vehicles, and there may not even be a steering wheel or what we traditionally perceive as vehicle controls in the vehicle. The big difference between level 4 and level 5 is with level 4, typically the vehicles are operating in well-known or well-mapped environments, whereas with level 5, vehicles are expected to operate anywhere that a human driver might reasonably be expected to operate, even if the vehicle has not seen the environment previously. Now, when it comes to modern autonomous vehicle development, we tend to not use the term car so much, because what we're effectively building has more in common with robotics development than it does with traditional vehicle development. There's a long history of vehicle development, and developing motor cars is a well understood field going back over 100 years. When we think about autonomous vehicles, and especially intelligent autonomous vehicles that need to make decisions in unknown and unfamiliar environments, it's better to think about them, or more productive maybe, to think about them in terms of robots. What's a defining characteristic of a robot? Well, robots have a long history as well, but autonomous vehicles are a type of mobile autonomous robot. And so the term robot originally translates from the Czech. The term robot was coined by a playwright called Karl Čapek, and first debuted in a play, literally in Prague in the 1920s. Since then, we've seen a lot of development in robotics. We've had, in the world of fiction, of course, Isaac Asimov coined the 3 laws of robotics. There's been a lot of development of mobile robot technology over the years. And one of the defining sets of characteristics of mobile autonomous robots is they need to be able to perceive the world around them, to make sense of the world that they're operating in, and to take action autonomously without human intervention. So when we think about autonomous vehicles, again, we're drawing a lot of influence not just from the world of motor car manufacture, but particularly from the domain of robotics and intelligent autonomous systems. Now, to enable a robot to actually see and operate in the world, it needs senses, just like humans have senses and animals have senses to help us operate in the world, where we have eyes and ears and haptic touch and other senses. Mobile robots and autonomous vehicles have a number of different sensors, the most popular of which include things like LiDAR units, which use light, radar units, cameras, things like GPS, motion sensors, other types of sensors. The main ones we'll think about for the purpose of this discussion are the LiDARs, radars, and cameras. Now, human visual range, you can see towards the top third of that picture in the visible spectrum of the frequency. You can see the visible light spectrum there. With autonomous mobile robots and autonomous vehicles, we're not limited to just the capabilities of human visual perception. One of the reasons we employ multiple sensors is to be able to see different things and take advantage of the strengths of different sensors. So cameras operate certainly in the range of the frequency spectrum that humans can see, but also we can leverage cameras to see a much wider range of frequencies than is possible with human vision. LiDARs operate around the infrared area of the spectrum, and you can see radars operate in much higher areas of the visual spectrum there. In terms of the types of data that are produced by these sensors, well, with cameras, we're all familiar with what camera images look like. Camera images then typically get stored as ones and zeros and binary data, numerical data in a computer. LiDAR and radar typically get stored and captured as something called point clouds, and you can see some examples on the right there. We'll come back to this notion of the types of data that we use to see and perceive the world in our autonomous systems a little later. Some more examples of how vehicles actually see and make sense of the world. So you can see on the top left there, an autonomous vehicle using radar and LiDAR and maps combined, and so they can see, they create what they call bounding boxes around the images, and so they can see here pedestrians with the pet, bicycles, car making a U-turn, lane changes, pedestrians crossing crosswalk. All of these things are possible to interpret using the different types of sensors that are provided on autonomous vehicles. From a software and a system engineering perspective, then, there's a number of different subsystems that we're interested in that make all of this possible. There are certainly cloud platforms and data platforms and remote services that operate in command centers or data centers. For the purpose of today's discussion, I'm going to focus more on the lower layers of the stack, so from the application layer down through the hardware. And from an application perspective, we're interested in 4 major subsystems. Localization helps autonomous vehicles understand where they are in the world. The perception system employs the sensors. So sensors are part of the perception system typically, and they help the autonomous vehicle to see and perceive the world and make sense of what it's seeing in the world. The planning subsystem then takes the output of the perception system and creates a trajectory so that it plots a course for the autonomous vehicle to travel. And then we have the drive-by-wire or the control subsystem, which takes the output of the planning system, that trajectory, and it actually steers the vehicle. It manipulates the acceleration, deceleration, the steering and controls of the vehicle to actually get it from a point A to point B. Then, as you would see in many different types of software and hardware systems, there's middleware. Different autonomous vehicle systems use different types of middleware and different operating systems, but typical characteristics of an autonomous vehicle is there will be some type of middleware system with capabilities including like system monitoring and logging, messaging, those sorts of typical services that you would find in a distributed system. There's operating systems, typically real-time operating systems and safety critical operating systems are essential for these types of systems. And then we have hardware that we'll talk a little more about later. So there are the physical sensors themselves, but there are also things like compute units that you find in an autonomous vehicle. And autonomous vehicles then are expected to operate in many different types of environments, and some of these environments can be more challenging than others, hence the need for many different types of sensors on a vehicle. So typically an autonomous vehicle company will decide carefully what type of environment it's expected to operate in. So for example, there's a big difference between operating a vehicle on a highway where it's long stretches of straight road and it's reasonably predictable, versus operating in an urban environment where the environment might be more challenging from a moment-to-moment perspective. Yeah, there's a lot of different traffic, pedestrians to deal with, traffic signs, traffic stops, roadworks potentially. So urban environments tend to be more dynamic and challenging from that perspective. So for those reasons, different companies will decide on different types of sensors to employ in their vehicles, and they'll place them all over the vehicle. And the particular configuration of these sensors tends to be a closely guarded secret in a lot of companies. Yeah, they'll decide carefully what types of sensors and where to place them for maximum effect to achieve their business and mission objectives. But the point here is that pretty much all autonomous vehicles will have multiple sensors located at different points around the vehicle. Some are intended to detect or perceive the environment in short range, some at medium range, some at long range. And typically there's a computer or a compute unit stored in the vehicle somewhere, very often in the trunk or the boot of the vehicle. Now, one reason we employ multiple sensors is that each sensor has its own different strengths and weaknesses. So, for example, radar is very good at detecting range or how far away something is. Cameras are very good at picking out the details of an object and have very high resolution, so we can distinguish, for example, between a person and a tree, or between the different types of traffic road signs that are on different roads. LiDAR then are very strong when it comes to things like estimating the distance or the distance accuracy to different objects on the road. Now, one of our challenges in developing systems with all of these sensors is taking advantage of all of these different strengths of different sensors. And we do that under a topic called fusion. So sensor fusion is something that we'll talk a little more about throughout the course of this discussion as well. So basically, when I talk about sensor fusion, it's about taking advantage of the strengths of multiple sensors so that we can leverage those sensors to best help the vehicle to operate in different environments. One of the challenges with all of that is that these sensors do generate quite a lot of data. So radar, for example, can generate up to 15 megabits per second per sensor. And if you've got multiple radars, that's multiple times 15 megabits per second. LiDARs could generate up to 100 megabits a second, cameras up to 3,500 megabits per second, and so on. And the resolution of these sensors is increasing all of the time. So in total, when you come, depending on the combination of sensors that a particular vehicle has, we could be dealing with anywhere up to 3 gigabits to 40 gigabits of data per second for the volume of sensors that the vehicle employs. And an interesting statistic here is that a single autonomous vehicle, when you think about all of this data, will produce more data in a year than the roughly 320 million monthly users of Twitter create combined. So if you think about all of the data from all of those tweets for a whole month, a single autonomous vehicle creates more data than that in a year. And if we multiply that by the millions of autonomous vehicles, you get some idea of the nature of the challenge in dealing not just with a single vehicle, but in aggregating the data from multiple vehicles. This picture offers a summary of some of those data points. So some autonomous vehicles typically could produce 4,000 gigabytes of data per day, with the majority of that coming from cameras, radars, LiDARs, ultrasonic sensors, GPS. And with improvements in the resolution of these sensors, that data can often increase as well. An additional challenge from an architecture and system design perspective that we have when in designing these types of systems is we need to be very aware of the environmental constraints of the environment under which the vehicle is expected to operate. So unlike some of the systems that I've worked on in different parts of my career, working with autonomous vehicles introduces these sorts of considerations. So for sensors or other hardware to be considered automotive grade, it needs to meet certain criteria. So for example, we need to be able to operate anywhere from minus 40 degrees Celsius to 125 or 150 degrees Celsius in some cases, which introduces some interesting constraints from a system design perspective. We also need to be compliant with many different standards. Those come from places like the Automotive Electronics Council or the Automotive Safety Integrity levels defined by ISO 26262. These sensors need to be supported by failure mode detection analysis and diagnostics. They need to support automotive specific communication protocols like CAIN or GMSL and different signaling interfaces. We'll talk more about those sorts of things later. But the main point here is in developing our hardware and software for these types of systems, there are a lot of constraints to enable these to be safety critical roadworthy systems that operate in environments where they're coming into contact with humans, with other road users, with pedestrians, with cyclists, with other vehicles. So it's critical that we meet all of these requirements as well. So for part two, let's look at machine learning in autonomous vehicles. How does machine learning relate to the world of autonomous vehicles? Well, I think most people, everybody I'm sure in this conference is familiar with deep learning. So I'm not going to go into any detail on the background of deep learning other than to note that when we talk about the deep in deep learning, we're really talking about representing successive layers of data in machine learning models. So modern deep learning often involves tens or even hundreds of successive layers of representation, and they're all automatically analyzing the data, and the layers typically are learned via models that we know or are referred to as neural networks and structured in literally in layers stacked on top of each other. So a well-known example of a convolutional neural network from the ImageNet classification paper a few years ago from Hinton and his colleagues shows an example of how an image recognition neural network is structured. And there's lots of variations on this sort of theme. You can see there are different inputs, different layers, and ultimately different classifications or different outputs from the neural network. How does this relate to autonomous vehicles? Well, if we're using a camera sensor or multiple camera sensors to see and operate in the world, we want to be able to take in an image, pass that image through our neural network so that each layer of the neural network ultimately learns different features of the image that it's seeing. And the output classification might be recognition of a particular type of vehicle, or it might be recognition of a pedestrian or a tricycle or a road sign or a tree, or any of the many different objects we might expect to encounter in an autonomous driving scenario. But ultimately, the input is an image. We pass the image through multiple successive layers of a neural network, and the output is some type of classification. Now, some additional examples here, we can see that we can pass in not just images, but also point clouds. So we talked about point clouds earlier as being the type of data that's captured by the LiDAR sensors or the radar sensors. So all of these different data types have their own characteristics, but we can pass them through neural networks so that the neural networks learn different representations about the environment within which the vehicle is operating. And so we can use the combination of camera data and LiDAR data and radar data and other sensors to get a more accurate and more holistic picture of the environment. So again, when it comes to software and the applications that are running our systems, we're interested in these primary four subsystems. So sensors that we've been talking about, the LiDARs, the radars, the cameras, perception, how do we see and make sense of the world, planning, how do we take the data from that perception system and plan a route or a trajectory through the world, and then control, how do we take that trajectory and actually move the vehicle so that it navigates successfully through the environment. And an example might be typically a vehicle might see a scene that involves a number of people in a particular location. So it will use a combination of the different sensors, pass the captured data through its perception system to create a model of the world, and it will see something like children playing ball near the road 15 meters ahead. It will take that interpretation of the scene that it's seeing and plan an appropriate trajectory that may involve slowing down or deviating course, and it will make sure then that that trajectory is passed to the vehicle's controls so that a safe journey continues. Again, different representations. We can use combinations of camera and LiDAR data, fuse that data so that the vehicle sees the world in a richer and more holistic way. So again, key points here are there are different types of hardware, different types of sensors that we're using to capture different types of data, so that we can combine that data in a way that takes advantage of the strengths of each type of sensor, and then move that data through our systems. And that introduces different challenges then for our software and hardware. There's a lot of evolution in all of these spaces. So the technology around sensors is continuously evolving. The technology around the compute platforms and how we deal with that sensor data is evolving. But the machine learning models themselves are continuously evolving. And one of the popular breakthrough models of the moment is something called a transformer architecture that emerged in 2017. So it's about 6 or 7 years old now at the moment, about 6 years since the paper was first published, but it continues to be highly impactful. And one of the key differences with the transformer architecture is that it's based on a simplified architecture that's based solely on something called attention mechanisms. So it stopped using things like recurrence and convolutions entirely to focus solely on attention mechanisms, so that it could bring in a notion of time awareness into the analysis of the data that it was analyzing. Now, transformers originated in the world of natural language processing and continue to find a lot of application in the world of natural language processing. So I think it's hard to escape all of the press around things like ChatGPT and BARD and other technologies that have been emerging. It seems like there's been an explosion in those technologies this year. But it's important to understand that technologies like ChatGPT basically are based on transformers, on transformer neural networks that are used to process text. So basically transformers have two parts. There's an encoder and a decoder. The encoder processes input text and the decoder generates the output text. So what does this have to do with the world of autonomous driving and the types of data that we deal with? Well, in the last 5-6 years, and particularly in the last maybe 2, 3, 4 years, there's been a lot of work on applying this very same architecture, the same technology of transformers to vision systems, for example. And so there are different neural network architectures like the DETR, the detection transformer, that treats basically object detection as a set of prediction problems. So using the transformer architecture, we can encode relationships between different elements that are captured in a scene. So on the bottom right there, you can see a disk to detect different road surfaces. So again, taking inputs, we can encode the different inputs captured from different road surface images, and we can generate a set of classifications from those different images. So again, an example of a technology that started in something like natural language processing and is being applied very much to image processing and autonomous vehicles. And again, just another example of how within autonomous vehicles we can use the transformer architecture to basically detect pedestrians and vehicles in a much richer way than is possible with other types of machine learning architectures. So a key point with all of that is that the space of machine learning and deep learning in autonomous vehicles, well, machine learning in general is evolving at a very rapid pace, and all of that technology, that evolution of technology and machine learning models is finding application within the world of autonomous vehicles as well. So part 3, let's look at some of the compute platforms, the software, the silicon, and the hardware that are powering our AI systems. Okay, right, just checking the chat. I thought there was a chat message there. So, okay, so there are 4 key trends in compute technology, and please do feel free to put messages in the chat window, and I'm happy to take questions as we go through this. When it comes to compute technology, there are 4 key trends that are important to be aware of. The first of those is the evolving paradigm of programming. So as software engineers, the literal paradigm of how we approach programming these types of systems is evolving. There's an ever higher performance demand placed on our systems, ever higher expectations of how our systems are intended to operate, and then ever higher capabilities of as we saw earlier, the types of sensors that produce different types of data. Then there's a lot of trends in the world of silicon and hardware engineering that as software engineers, it's important for us to be aware of. And we'll talk about that in context in a moment, because that gives us many opportunities for how and where the code that we create for these autonomous systems executes. And then the fourth trend that we'll look at is the complexity of our software engineering ecosystems. How do we manage all of these different technologies in a way that helps us still be productive and create reliable, predictable systems? So the first thing we'll look at is the evolving paradigm of programming. And from a procedural classical programming perspective, we're accustomed to a model where we specify rules, program those rules, we take data, we create programs or write programs that produce answers, and then we validate those answers. With machine learning, we know that we flip that around a little bit. Data now becomes central. So we take lots and lots of data and feed that to our system, and we train our system using, in some cases, predefined answers, the answers that we're looking for. So through the combination of answers and data, we're helping our machine learning systems to learn the rules by which they operate. So that's a change that I think at this stage, many of us working in software engineering have accepted that this is part of the new paradigm of developing systems in the machine learning age. But it brings difficulties. Machine learning bugs then are much trickier to identify and resolve. In traditional software, we get an error or a bug. We can see we can often see the effects of the error. Not always, but very often we can see the effects of an error pretty readily. In the new paradigm of machine learning development, rather than an error, sometimes what we get is degraded system performance, and it's not always easy to specify in advance what an ideal performance is. So recognizing degraded performance, especially if it's happening gradually over time, can be very difficult. So machine learning debugging, machine learning identification of problems is a key area for us to focus on. Now, with all of this evolution of technology, the notion of what it means to be a full stack developer or a full stack engineer in the world of application and product development is continuously evolving. So if you're working in a domain of web development or app development, maybe full stack might include HTML and JavaScript and CSS, or it might include some other technology like Python or Java on the back end, or JavaScript on the back end. When we're dealing with the autonomous systems and in particular autonomous vehicles, it's useful to think about the stack of technologies in terms of algorithms, software, and compute hardware. So from a software perspective, if we start at the middle there, from a software perspective, we're used to dealing with frameworks. With the world of machine learning development introduces many more frameworks and libraries that we need to be proficient with. Some of the popular choices when we're developing machine learning models, for example, come down to a choice between PyTorch and TensorFlow, maybe using some other frameworks like XGBoost. Then there's a range of libraries for dealing with the types of point cloud data that I talked about earlier, or dealing with the different mathematical convolutions that we need to deal with when dealing with very heavy numerical data from the different sensors and other machine learning models that we're dealing with in the vehicles. And so quite a range of software applications to be familiar with. And the ones I'm highlighting here tend to be some of the more popular ones that I would typically lean to in these types of environments. There's a lot more, of course, which we'll look at in a moment. Then from an algorithm perspective, as we talked about a moment ago, the world of algorithms is continuously evolving. So with an autonomous vehicle, we're not using just a single algorithm. We might be using different types of vision algorithms to do object detection. So for example, we might use something like SSD or single shot detection, or YOLO, you look only once, to identify the content of an image very quickly, or as quickly as possible. We might use Hydra nets or point nets or lane nets or voxel nets to work with LiDAR data or radar data or fusion data that we talked about earlier. Or increasingly, we might use different transformer architectures. But the point here is, as software engineers working in these types of environments, we have to stay current with the state of the art on algorithm development in the autonomous vehicle and autonomous system space, as well as the software frameworks. And then, the third piece of this, the bottom piece, there's a lot of different hardware components and connection protocols that come into play when we're dealing with these types of systems. We'll look at some of the accelerators in more detail in a moment, but some of the connection technology or protocols that we need to be familiar with are things like Ethernet, which we would be typically familiar with anyway, but also autonomous vehicles introduce a whole new, a whole range of different communication protocols and connectivity protocols that have different advantages and different use cases. So PCIe or GMSL, for example, are popular connection protocols for connecting sensors in an autonomous vehicle or for connecting different components within an autonomous vehicle computing system. And of course, the range of possible choices can be mind-bogglingly large. This is just one example of the myriad of different technology options that are available from the Linux Foundation and their AI and data landscape. This is a recent snapshot of their AI and data landscape, and it is continually evolving. And it certainly doesn't represent everything that engineers and scientists and roboticists and data scientists in an autonomous vehicle environment need to be aware of, but it's a good reference point. And again, a key point here is the challenge of keeping up to date with the evolving state of the art in the different technologies that are available and how we might use them in autonomous vehicle development. The second trend is the ever higher performance demands that are placed on our systems. So this is a picture I like from Ray Kurzweil. He talks about the law of accelerating returns, and the vertical axis there, the y-axis, represents the number of computations per second per constant dollar. So he has a mechanism of just normalizing the dollar over the course of the last 90 years or so, so that we can understand how the price performance of computation has increased dramatically in the last 90 years, so that the amount of computations we get per second for our dollar is many orders of magnitude greater per decade than the previous decade, and that trend is set to continue for at least the next few years. And with the introduction of things like quantum computing, I'm sure the landscape will shift dramatically again. But the key thing for us to be aware of right now is, how do we harness this price performance scale when designing our systems? How do we take advantage of that? Second thing to be aware of is performance of the different technologies that we use in our different software development environments. So if we take Python as a baseline, then typically, we'll use Python for model development and maybe for a lot of offline, off-board activity, so off of the vehicle. Things like PyTorch or TensorFlow are great technologies for using Python code to test out and develop our machine learning models. But when it comes to running code on the vehicle itself, it's typically going to be C or C++ code that's on the vehicle, not Python. And at a minimum, we're looking at at least 47 times 47x speed up of execution in the performance of the code. And of course, execution speed is not just the only consideration. There are also other factors like safety and robustness and reliability of the language. But for the purpose of this slide, we'll focus on execution speed. If we introduce parallel loops or memory optimizations, we can see that the performance increases we can get in a language like C or C++, it goes to orders of magnitude increase. So it's really not a competition at all for considering which language to use. And then if you're using something like like an Intel architecture, you might use SIMD instructions to take advantage of specifics of the Intel CPU chipset. There are similar instruction sets for an ARM CPU instruction set, for example. But you can see again, there's an order of magnitude increase in performance when you bring in things like CPU-specific optimizations to your code. So again, these are all things that we need to be aware of, because one of the key measures that we have for safety and success in autonomous vehicle development is what we refer to as latencies, or simply the end-to-end time it takes for the vehicle to process a signal from the time photons hit a sensor, whether it's a camera sensor or a radar sensor or LiDAR or something else, to the time at which the vehicle makes a decision to accelerate, decelerate, or turn. So we refer to that as the end-to-end latency. And if we think about things like a cut-in scenario, if a vehicle cuts in front of your vehicle or a pedestrian steps out onto the road, we want that reaction time to be absolutely as fast as possible, and to be not just comparable with human level perception, which is on the order of maybe hundreds of milliseconds, but we want it to be faster than human level perception to optimize for safety and responsiveness. So all of these measures become safety critical in that context. And then the number of operations that we can perform on our machine learning systems over time is doubling. It seems like it's doubling every 6 months or so. So this introduces, again, the capability that we can train ever complex models, ever more sophisticated machine learning models with ever larger amounts of data in shorter amounts of time, if we can take advantage of these trends in training compute times over time. So the third trend then that we'll talk about is the range of compute options that exist for our code. So typically, if we're working with developing a model in something like a Jupyter notebook or an IDE, we might typically think about running our code on the CPU first, or maybe a GPU if we've got one available on our local developer workstation. It's pretty straightforward to get GPU access in one of the cloud providers like AWS or Google Cloud. But those are two of many different options that are available to us to execute our code, and they're not always the right options. So it's important as system designers and software engineers that we understand the range of options that are available to us. CPUs are on the spectrum here, are absolutely the most flexible of options that are available, but they're also the slowest, depending on the type of operation that we're looking to perform. GPUs, which have their origin with NVIDIA and the world of graphics, turned out to be ideally suited to perform the types of matrix multiplications and other mathematical calculations that are a natural fit for machine learning models. And they certainly have their place and provide huge performance boosts and increases, particularly with things like convolutions and convolutional neural networks. But again, they're not the only option. They're a big improvement and increase in performance and efficiency from CPUs. But for the types of applications that we've been talking about so far, like safety critical, different modalities or different types of data being combined, it's useful to think about different types of silicon and hardware that are available to us. And typically there are different options with different types of silicon and different ASICs that we can look at. Some of the most popular are things like vision processing units that are ideally suited to vision-based applications, tensor processing units, which take more general mathematical structures than just pure matrices and are optimized for processing tensors. And then there's a lot of emerging technology around things like neural processing units, which can be optimized for different machine learning models and different neural operations that those machine learning models perform. So in a typical modern autonomous system environment, we don't necessarily use just one of these technologies. We run different workloads or different applications on a range of different processing units. So central processing units are still core to any type of computing system in this environment, but the other types of processing units also have their place and enable advantages when we're thinking about how do we run different types of machine learning models in those sorts of environments. An architecture trade-off example bringing all of that together is thinking about our entire system of sensors and hardware and software and middleware and the different options we have for executing our models, whether it's CPUs or neural processing units. Yeah, we got to think about our systems as being a distributed system. So literally within the vehicle, think of the system itself as being a distributed system where different nodes, whether it's sensors or compute units or processing units, are connected through different bus links. It could be PCIe, it could be Ethernet, and using different protocols like maybe GMSL or CAIN to communicate together. All of those imply different performance trade-offs, different connectivity trade-offs. And one of the kind of key decisions that you might have to make in a system like this is whether to co-locate your computing capability with your sensors, or whether to distribute your computing capability at different points around the vehicle, or whether to distribute your sensors at different points around the vehicle. How close to place your sensors and your compute technology? Where should your code run in relation to the different sensors and where they're located? So all of these are architecture constraints and trade-offs and considerations that we need to be constantly evaluating. Then the fourth trend when it comes to computing systems is the complexity of our software engineering ecosystems. So machine learning systems, we know, require extensive testing and monitoring. So not just analyzing our data or training our models in the cloud, we need to specifically think about the runtime environment of our machine learning models and how they're being executed on the vehicle. How do we build in things like monitoring and testability and logging and other things so that we can understand the performance of our machine learning models in real time as they execute on the vehicle. And so that brings in a whole lot of different considerations for engineers. So things like machine learning infrastructure tests, data monitoring tests, those sorts of things that we didn't have to consider in a non-machine learning or a non-AI environment now become critical, as well as the more traditional tools at our disposal, like unit testing and integration testing and different types of monitoring. But it all becomes very complex to deal with in an environment or a system like this. It's pretty much a classic paper at this stage, I think, but it still summarizes the challenge quite well. So when we think about the proportion of the code in our systems that is machine learning specific, it's still a proportionally small in terms of volume amount of code for what goes on in the overall system. So we still need a lot of engineering around configuration management, data collection, monitoring, machine learning management, feature extraction. All of those things still need to happen in the context of an autonomous system. The machine learning code itself is absolutely critical, but it's important to keep in mind it exists within the context of a much larger system, and that system also needs to be managed from an engineering perspective. This picture puts that proportion into perspective as well from the point of view of the different types of challenges that we face in developing these autonomous systems. So a lot of our challenges still relate to things like software quality, data management, project management, infrastructure, architecture design, AI engineering. Yeah, it's not just challenges related to model testing and model performance. All of these different challenges need to be addressed for a successful, holistic ecosystem of developing autonomous systems. And so evolving DevOps to manage our machine learning systems is critical. Continuous integration is not just about testing and validating code. Continuous deployment is not just about a single software package or a service, but an entire system. And continuous training is something that we need to bring into our machine learning systems in order to continually evaluate the systems and the models that we're developing. And so from an ML ops perspective, a typical workflow might look something like this. Again, I'm sure that everybody in a CAIN audience is familiar with a typical ML workflow. But there are some, from a typical DevOps workflow, it introduces some new steps like model training, model evaluation, and so on. That's important for us to incorporate into our overall development lifecycle and have the tooling and infrastructure to automate all of this. So again, machine learning ops is an absolutely critical cultural and technology practice that's essential to the success of any organization operating with this broad range of technologies and challenges. So in part 4, the final part of this keynote, let's look at bringing all of these things together in the context of enabling AI-enabled systems, or software engineering for AI-enabled systems. So if we look back over everything that we just talked about, what is an autonomous vehicle? Well, it depends. It depends on the perspective that you take. So from one perspective, an autonomous vehicle is a transportation solution. From a technology perspective, there's a whole lot of other things that an autonomous vehicle is. It's a distributed system. It's a data center on wheels. It's a real-time embedded system. It's a mobile robot. It's a safety critical system. And really, it's a complex system of systems that's operating continuously in a dynamic and ever-changing environment. So from a software engineer's perspective, what does this all mean? So as software engineers, we have a solid foundation of theory and practice and research in the world of software engineering that is absolutely foundational to autonomous vehicle development. And in addition, to be successful in designing and developing autonomous vehicle systems, we also need to stay abreast of developments in machine learning and data engineering and data science and hardware, as we saw in silicon development, and robotics. So part of the joy and beauty of autonomous vehicle development is if you enjoy technology, if you enjoy tough problems to solve and challenging problems to solve, and enjoy having an impact with that technology, then autonomous vehicle development is a very rich place to be. And I hope throughout the course of this keynote, I've convinced you that many of the most interesting and impactful developments in machine learning today, and indeed in software engineering today, are happening in the domain of autonomous vehicle development. So let's think about CAIN for a moment in a little more detail. So we're gathered here in the second international conference on AI engineering and software engineering for AI. And CAIN has a number of different goals over the next few years to help us collectively as a community of engineers and scientists and practitioners and researchers and educators to evolve the world of AI engineering and software engineering. So in looking through this year's representation of CAIN, a few things stood out to me. Overall, I mean, all of the contributions are fantastic to this year's conference, but I wanted to take a moment to relate some specific papers that have I felt a direct correlation with some of the things that I've been talking about today. So in a data source dependency analysis framework, the authors here talk about dependency hell, a well-known concept in software engineering for many decades, but the authors have taken that concept and really enriched it to help us understand the implications of not dealing with dependency hell and the dangers of that expanded dependency hell in the complex types of machine learning systems that we're developing. So a lot of good guidance here from the authors on their dependency mapping framework that allows ML ops engineers to monitor the whole dependency map of their models. And I look forward to digging deeper into this in the coming days and weeks. Another paper that I'll just call out here is the meta summary of challenges in building products with ML components, where the authors have identified a very broad range of challenges across almost 5,000 practitioners developing different machine learning systems. And they summarize those challenges very nicely in the paper. I've just taken a summary of their summary here for ones that resonate particularly for the types of systems that I'm involved in developing. It's great to see a focus on things like architecture, design, and implementation challenges, model development challenges, data engineering challenges, quality assurance challenges. And the paper goes into a lot more detail on these and other challenges, including things like project management and process challenges, which are also vitally important to be aware of. But also being aware of these challenges and how other practitioners are addressing them is a very useful reference for industry practitioners. Hyperparameter tuning, again, optimizing the systems that we're developing is a key goal. I mentioned latency optimization as a key goal in achieving safety and responsiveness in our autonomous vehicles. Part of the key to that is optimizing the system at different levels. So we optimize the code, we optimize the silicon, the compute paths through the compute system. But also very early on in the machine learning development life cycle, we have an opportunity to use hyperparameter tuning to optimize the models themselves as we're training and developing them. What I found fascinating in the insights in this paper is the degree to which practitioners are not taking advantage of hyperparameter tuning to optimize their models. And so there's a large range of findings in this paper. Ones that stood out in particular are very few of the available hyperparameter tuning options are currently being used by practitioners. So I found that incredibly insightful. And very useful. And then one more that I'll call out in relation to computer vision is a paper that's looking at the engineering challenges for computer vision systems. Now, this paper I know focuses on aerial systems and drone-related technology and unmanned aerial systems. But I found a lot of the lessons learned and guidance in the and proposed solutions in the paper to be equally applicable to land-based autonomous vehicles as well. So again, very useful and insightful stuff. And again, in the role of performance improvement, it's great to see research and recommendations on model quantization and a framework, a practical framework that I'm looking forward to digging into more to help us produce more reliable deep neural networks. With that, we'll start to draw this to a close. I like the Heraclitus quote that no man ever steps in the same river twice, for it's not the same river and he's not the same man. Again, very relatable in terms of our journey through life. I like to paraphrase that in the world of autonomous vehicles and say that no autonomous vehicle ever drives on the same street twice, for it's not the same street and it's not the same vehicle. We operate in an environment that's continuously changing and evolving, and that challenge is part of the motivation for all of this research and practice. With that, I'll hand it over to Helena.
Thank you so much, Ken. I am overwhelmed. Well, thank you for sharing some of your great experiences with us. And as I said, I am overwhelmed not only with the details and the experiences from the domain in which you operate, but also on the level of detail in which you have related to some of the papers that we will actually have the opportunity to listen to at this year's conference. So amazing, and thank you so much. And if everyone could do this, this is what we are doing. So we have time for questions, and I already see hands raised. And I think the first hand I saw was from Jan Bosch.
Yes.
Hello, Jan.
Hey, Ken, first of all, I have to agree with Helena. Amazing presentation. I loved it, and I really loved the depth in which you went into the whole engineering process and how holistic you were, that you didn't only talk about the software or the machine learning, but you took actually everything into account. The question that I wanted to ask you is concerned with certification, which I'm sure is one of the topics that I don't think you brought it up very much, but it's one of the key things that the automotive companies in the Gothenburg region are struggling with. As you probably know, we have a few companies starting with Volvo in this area. We also have Scania. We have some Chinese competitors that are doing a lot of engineering work here in the region. And the question that they are all looking at is, how do we get to DevOps of all our safety critical software in our vehicles, while at the same time staying compliant to ISO 26262? And I know that Tesla doesn't use it. I don't know what you and your company are using in this context, but I'd love to have your take on how to think about certification and what you think the right approach is.
Sure, absolutely. Thank you, Jan, and thank you for your comments as well. Very grateful. So on the topic of certification, it's essential. There are a range of different standards. I referred very briefly to something called ISO 26262 and automotive safety integrity levels and some things like that. But those are important standards for us to adhere to as we develop the different components and systems. And there's also life cycle models that are critical for ensuring the safety of the systems that we're developing. Just given the nature of just given the constraint on time that we have, I'll refer briefly to this. As a company, we've put a lot of work into developing a software, not just a software, sorry, but a system development lifecycle model based on all of these standards that's both practical and meets the legal and regulatory and safety requirements of different jurisdictions. And that entire lifecycle is open sourced, so you can actually find it on GitHub. And I was not involved in this. My colleagues have developed this. But it's one of the many resources that we've shared quite openly. So I'd be happy to point a link to that offline. That's one part of the answer. There are different models like automotive spice and other things. And then, as you know, different jurisdictions, if you're deploying your technology in the US, even different states have their own regulations that we need to comply to. Europe is developing different regulations. The Chinese market is developing different regulations, and these are constantly evolving. So, so it's not just a technology problem. There's a public policy challenge and a regulatory challenge as well that we absolutely have.
If I'm allowed to ask one quick follow-up question.
Sure.
When will we see the first fully autonomous vehicle in a limited ODD used in commercial deployment?
So different companies, including ourselves, already have that on the road. I didn't include press releases in the presentation, but it's easy to find if you search for like the Las Vegas partnerships that we've got, for example. And there are other companies that are deploying in different regions like San Francisco or Phoenix. So one of the things I will call out though is like and again, I celebrate the success of every company that's operating in this domain and the tremendous challenges that they're overcoming. But operating in a highway, in a sunny open road, is comparatively more straightforward than driving down the Las Vegas Strip at night with thousands of revelers and other vehicles and roadworks and very unpredictable environments. So it's already happening is the short answer, and will continue to expand.
Wonderful. Thank you very much. And Helena, back to you.
Or the Irish roads, to say the least.
Oh, yeah. Well, absolutely. Yeah, that's a whole other challenge, Helena.
They are narrow. Hey, do we have other questions from the audience? Even if it is a little late for some people or early for others, but this is super interesting. I see Henry turning on his camera.
Hey, Henry.
Hi, Ken. Nice to see you again. So thank you very much for the talk. In terms of architecture and how to distribute the computation, the data, and the different steps in the learning and execution part, do you see, space of improvements, what is done today? And, because you were saying that, I remember from your previous presentation to the workshop last time that there is an internal computer in the trunk of the car, but I expect also that some computation can be in the street with some edge computation, something in the cloud. So what is, in your understanding, the current situation? What can be in the near future in order to make a more distributed computation, also to support, as you said, this increasing amount of data and power that comes to more precision and more gigabytes because you want to get more data. So what do you think from this architectural perspective?
Yeah, so a lot of that is constrained by what Jan was asking about in terms of standards and regulations, and also by safety. So you're absolutely right. There's a range of different elements in the ecosystem, on the vehicle and off the vehicle, and in the cloud, and in the urban infrastructure around the vehicle potentially, and other vehicles themselves. And technologies like V2X, vehicle to anything, or 5G, or emerging technologies around 6G, enable a lot of really fast communication. But it's still, from a regulatory point of view, and even from just from a safety point of view, any decision that the vehicle needs to make that potentially affects lives or affects how the vehicle operates in an environment needs to be made on the vehicle. So we want decision making to be as close to the point of perception as possible from that perspective. So even though off vehicle connectivity is fast, it's not reliable enough for the sort of safety critical use cases that we need to deal with. From another perspective, there are, of course, things like infotainment use cases, which are perfectly valid to think about things like 5G and 6G technology. It's okay if there's a lag in downloading your favorite playlist or something like that. It's not okay if there's a lag in deciding what is that object in front of me? Is it a shadow, or is it a cinder block? Do I need to stop? So those different decisions will affect where you place the decision-making capability and which technologies you use. Does that start to answer your question, Henry?
Oh, yeah, absolutely. Even the training is done on board, or the training is done, somewhere else, and then the model is uploaded into the car? How it works from the training part?
Yeah, so from a training perspective, exactly. Training is done typically in a data center, and the model then is deployed to the vehicle and executed on the vehicle. And yeah, at this point, I don't think any company would do model training or retraining on the vehicle itself. We certainly collect lots of data on the vehicle, as you saw in the presentation, but that data then is transferred to an off-board environment, like typically a data center or a cloud environment, for processing and for model training and for analysis and things like that. So there's a very rich cloud infrastructure around all of this.
So this means that there is a huge possibly is sent by the car into the cloud for recomputing or adapting the model and back.
So I missed there was a slight break in your question, Henry. Can you just repeat that?
Okay. Yeah. The question is, if I correctly understand, indeed decisions are taken locally, but if you train the model, then you need to send the data, big amount of data from the car to the cloud, retrain, and then upload the new model into the car, and while it's operating, making decisions.
We typically, so again, it depends on the use case. We typically wouldn't update the model while it's in operation, while there's a passenger in the vehicle. You would typically update the model at something like an operation center and thoroughly test the new updates before letting the vehicle back on the road again. So there is a life cycle around all of this. That's we want to minimize that life cycle as much as possible, reduce the cycle time as much as possible, but also we want to make sure we are still being safe, and that the model, in combination with everything else that's running on the vehicle, has been thoroughly tested and evaluated. So we wouldn't update a live running vehicle in that context.
Clear. Thank you very much.
Sure.
Thank you, Henry. And I see that there is a question being typed in the chat from Andrei. Ken, he asks you to say something about the quality assurance pipeline. How much simulations versus real life environments are used? And maybe you see his comment in the chat.
Yeah, I'm reading the comment now. Thank you, Andre.
Yes, thank you.
Okay, so simulations are again an essential part of the overall system development lifecycle. So we use simulations. I'm sure every autonomous vehicle company that I'm aware of uses simulations. Sometimes that's a combination of simulation tooling that they develop themselves, or there are also commercial solutions for simulations. But what a simulation, one of the key advantages of using simulations is that it allows you to create scenarios that you may not be encountering when you're driving your vehicle. So when we're driving our vehicle, we're capturing data all the time, and we can train our models based on that data, but we're limited by what we encounter in the real world. With simulations, we can, you can simulate like a 200-foot gorilla cycling a tricycle. You can simulate what happens when 5 cars suddenly appear in front of you. You can simulate different weather conditions, different road configurations. You're no longer limited by the scenarios that you encounter in real world driving, and that allows you to develop a whole range of responses. So one of the key things in training and retraining our models is the idea of novelty. There is little compounded value in capturing data that shows yet another sedan vehicle pulling in front of you and you slowing to avoid it. That's a typical scenario that you might encounter hundreds of times in a day, thousands, tens of thousands of times in the life of a vehicle. There's a lot more value in teaching the vehicle how to respond to novel scenarios, and you can better create, or you at least have more flexibility in how you create those novel scenarios, through simulation. So, somebody skateboarding, somebody on a tricycle, those sorts of things are less common, but we still need to, as humans, we would know intuitively how to respond to them if we encounter them, but we have to train our models how to respond to them. And in terms of life cycle, so we have like continuous integration, continuous deployment environments, machine learning operation type environments, and simulations are integrated into that overall workflow of from, I call it from code to road. There's a pipeline of activities, including simulations, that are part of that.
Thank you so much. And Andrea, I hope that you feel you got the response to your questions that you asked for. And thank you so much, Ken. Is there anyone else with anything else you would want to add at this point?
I might have a question.
Justus have a question.
Hey.
I was wondering if ethical questions or challenges play a big role. So I remember a few years ago, public backlash against a German car manufacturer, where an executive publicly stated that they would try to prioritize the lives of the drivers in situations where a decision has to be made. So do such questions play a role at all currently at your company?
The question of ethics in general, absolutely, as it should, I would argue, in any company developing technology that has the potential to impact lives. Absolutely. The particular example, though, I mean, we're developing vehicles that don't have a driver, so that particular example wouldn't necessarily apply. But safety, we say for a reason. Safety is our bedrock. All of the decisions we make from both a business perspective and a technology perspective, absolutely, in deciding what capabilities to develop is built on a foundation of safety first, and that's more than a slogan. I mean, that is absolutely entrenched as part of the culture of the company and how we develop systems. But yeah, again, I would argue an ethical framework has to be a guide for any company developing this kind of technology.
Thank you.
Thank you so much for the question, Justus, and thank you so much, Ken. I think in the interest of time, we close it here. Thanks a million, Ken. I think this was the best possible way to end the first day of CAIN 2023. Really, really interesting, and thank you so much.
Thank you so much,
said,
Helena.
this was the first day, and I'm going to invite my co-chair, Ipek, and also the general chair, Jan Bosch, if they would want to say something about the coming day. But to close this off, thank you, Ken. Really nice.
My pleasure. Thank you so much, Helena, and thank you, everybody.
Wonderful.
You.
Yes, absolutely. Applause, Ken, from all of us. I'm not sure if Ipek is still awake. She is in Australia after all, but Henry is at least still here. Tomorrow morning, we all start with the second keynote of this conference, which is by Futse.com, who will talk about, and now I have to check the calendar because I just missed it. But he will talk about, refresh my memory, Helena and Ipek. What is his topic again? It was reliable AI or something.
The title of the talk is Engineering Trustworthy AI
Trustworthy,
Systems.
that's it. That was the one word I couldn't think of right now. So we start at 9 o'clock, we run until 15:30 again tomorrow. And for everyone who thinks, that is curious who will be getting the awards, make sure you stay until the very end, because we're only announcing awards in the closing session tomorrow. So we start with a great, not a great keynote, although Futse will have to work pretty hard to outdo Ken's amazing delivery, I think. And then we have paper sessions, a panel, and then the closing of the online part of the conference. And of course, for all of the people that are in Australia, you still have the on-site part of CAIN then waiting for you on the 20th. So with that, we're going to close for today. Thank you all very much for participating, and I look forward to seeing all of you tomorrow at 9 o'clock sharp after a fresh workout, or for the people in Australia, a full day conference that they then get to combine with the second day of CAIN. So with that, thanks a lot, and I look forward to seeing you tomorrow. Bye-bye.
Bye.
Thank you. Bye.
Thank you, Jan. Bye. Thanks, everybody.